Right now, if you're listening to this through headphones, more than 99% of the sound wave that once existed in the real world is simply gone. Deleted. What you're hearing is not the original wave, it's a ghost, rebuilt from a handful of numbers spaced fractions of a millisecond apart. And somehow, your brain can't tell the difference. This is sampling, the quiet mathematical trick hiding inside every song, phone call, and video you've ever streamed. In signal processing, sampling is the process of reducing a continuous, ever-flowing signal into a discrete set of individual values, snapshots frozen in time. A sound wave rolling through the air becomes a sequence of numbers called samples. Each sample captures the wave's exact value at one specific instant, then the wave keeps moving without you. It sounds almost impossibly lossy. Yet this is the foundation of every CD, every MP3, every digital photograph and video ever made. A sampler is the device or process that actually grabs these values, an analog-to-digital converter listening to a continuous signal and freezing it, over and over, thousands of times per second. A theoretically perfect sampler would capture the exact instantaneous value of the wave at each chosen moment, with zero error. In reality, no sampler is perfect. But the theory behind the ideal sampler is what makes digital sound and video mathematically possible at all. Here's the part that sounds like a magic trick. From that sparse set of frozen numbers, the original continuous wave can be rebuilt almost perfectly. It's done through the Whittaker-Shannon interpolation formula, which mathematically behaves like passing the samples through an ideal filter. Engineers picture the samples as a row of infinitely thin spikes, a Dirac comb, that gets smoothed back into a flowing wave. In other words, silence between samples isn't lost data. It's data waiting to be reconstructed. How many snapshots do you need per second to fool the human ear or eye? The answer is measured in the sampling rate, the number of samples captured every second, expressed in hertz. A standard audio file might use 48,000 samples per second, meaning the wave is frozen and measured 48,000 times before you even finish saying 1 second. The higher that number, the more faithfully the digital copy can imitate the original. But here's the twist nobody warns you about: there is a hard, mathematical wall you cannot sample past. It's called the Nyquist frequency, and it sits at exactly half your sampling rate. Any detail in the original signal that changes faster than that limit, packed into less than 2 sample intervals, cannot be captured correctly. Cross that invisible line, and reconstruction doesn't just get blurry. It lies to you. To keep that lie from happening, engineers hide a silent gatekeeper in front of nearly every sampler, the anti-aliasing filter. Its entire job is to strip out any frequency above the Nyquist limit before sampling even begins, because once those too fast details slip through, they can never be separated out again. Skip this filter, and the reconstructed signal doesn't fail loudly, it fails quietly, disguising itself as something that was never actually there. This disguise has a name: aliasing. And you've almost certainly seen it with your own eyes. Watch a spinning wagon wheel or helicopter blade on camera and sometimes it appears to freeze completely still, or even spin backward, even though it's spinning normally. That's aliasing in the wild. The camera's sampling rate is too slow to keep up with the motion, so the footage invents a false, slower motion that was never real. The same ghost shows up inside sound. When a sampler is fed a tone above the Nyquist frequency, it doesn't just fail to record it, it records a completely different, false pitch that folds back down into the audible range. Musicians and engineers call these phantom tones aliases, and once printed into a digital recording, they're indistinguishable from a real note. There is no filter that can undo them after the fact. The only cure is prevention, before the first sample is ever taken. So far, this has all sounded like clean, elegant math. Real hardware is far messier. In practice, sampling is carried out by physical analog to digital converters, real circuits, wires, and capacitors, each with its own limitations. The gap between the theoretical ideal sampler and the physical device sitting inside your phone is exactly where a hidden family of distortions is born, quietly reshaping every recording you've ever made. The first hidden flaw is called aperture error. A real sampler doesn't capture a signal's value at one perfect, infinitely thin instant, it averages the signal over a tiny window of time, because the capacitor inside the circuit can't track a changing voltage instantly, and can't isolate itself from that voltage instantly either. The result is a sample that's technically blurred, capturing a smeared average instead of a true, frozen point. Then there's jitter, the sampler's sense of timing itself going slightly wrong. Ideally, samples are captured at perfectly even intervals, like a metronome with zero deviation. But real clocks wobble by fractions of a nanosecond, and every one of those tiny timing errors gets baked permanently into the data, subtly distorting a signal in a way that can't be heard as one obvious glitch, but as an accumulation of imperceptible smears. On top of imperfect timing comes noise, thermal noise inside the sensor itself, electrical interference in the surrounding circuitry, and random fluctuations that have nothing to do with the signal being measured at all. This noise doesn't announce itself. It simply blends into every single sample, forever indistinguishable from real signal once it's been captured and stored. There's also the slew rate limit, a hardware ceiling on how fast the converter's internal voltage is even allowed to change. If the real signal moves faster than the circuit can physically follow, the ADC simply cannot keep up, and the recorded sample falls behind the truth, lagging just enough to quietly corrupt fast-changing sounds or signals. Finally, there's quantization, perhaps the strangest limitation of all. Every sample must be converted into a number, but computers can only store numbers with finite precision. That means every single sample gets secretly rounded to the nearest available value, discarding whatever tiny fraction didn't fit. Multiply that rounding error across millions of samples per second, and an entirely new form of distortion emerges from nothing but arithmetic. And even beyond quantization, converters introduce their own nonlinear mapping errors, small inconsistencies in how input voltage translates into an output number, errors that have nothing to do with rounding at all. Layer aliasing, aperture error, jitter, noise, slew limits, quantization, and nonlinearity together, and you get the full, messy reality behind every clean digital recording you've ever trusted. Engineers do have a partial fix: oversampling, sampling far faster than strictly necessary, which can push aliasing and aperture error out of the range anyone will ever notice. But oversampling has its own ceiling. Push it above a few gigahertz and it becomes physically impractical. Push it lower down and it can still be prohibitively expensive. Even then, oversampling reduces quantization error and nonlinearity, it can never make them fully disappear. Which means every piece of digital audio, video, or imagery you've ever experienced is not a perfect copy of reality, it's an extraordinarily good forgery, built from frozen instants, invisible filters, and mathematically managed errors small enough for your senses to forgive. The wagon wheel that spins backward, the phantom tone hiding in a recording, the silence between samples that somehow isn't silent at all of it is sampling, working exactly as designed, and lying to you just enough to sound true. So the next time you press play, remember, you're not hearing the real world. You're hearing a beautifully engineered guess about it, thousands of guesses stitched together every single second. If this cracked open a part of the digital world you never questioned, subscribe to Wait, What? Because the next hidden trick behind your screen is just one video away.